Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. In today's video we're going to look at a special sequence that was studied perhaps first intensively by Gottfried Leibniz. It's associated with harmonic sequence or series, and it's just the sequence of reciprocals of natural numbers. And this will give us an occasion to introduce some discussion about the algebra of sequences, and in particular an important formula called summation by parts that will then apply to find a rather mysterious and wonderful formula associated to this. Okay, so a good place to start is with this sequence and to try to understand it, to create a difference table. Now this is not a sequence of natural numbers or integers, so it's a little bit of a departure, but it's still a very interesting kind of sequence to analyze. So here's a difference table, and the sequence here is down the first column. And note how I've set up the difference table. So we have indices here, typically n and k over here, and the actual entries are the kth differences and the nth elements in those kth differences. So there's the original sequence, there's the first difference, the second difference, the third difference, and so on. And the table carries on like this. Okay, so what do we notice about this? Well, it's some kind of symmetry involved. First of all, the table appears to be kind of symmetrical. There's these minus signs down every second column, but otherwise there's a kind of a symmetry. And if we examine it a little bit more carefully, we'll notice that there's a nice pattern to it. And so if you're a student here, I think it'd be a great thing to stop the video and to just stare at this table for a little while and see if you can see what the pattern is, in terms of being able to write down the formula for the general entry in the nth and kth positions. So have a go at that. Okay, so now let's see if we can do that. So going down to row n and across to column k, what is the entry? Well, the first thing that's kind of clear is that the signs are only dependent on k. So there's going to be a -1 to the there's -1 in the first, third, fifth, so we should put -1 to the k here. That will take care of the minus signs. And then we can look along these sort of off diagonals. That's sort of the key to things. So let's say we look at this diagonal here, 1/3, -1/6, 1/3. And we just look at the denominators involved because all the numerators are all 1. So if we just look at the denominators, we see 3, 6, 3. So there's a common factor of 3 there, and if we pull that out, we would get 1, 2, 1. Okay, if we go to the next diagonal and pull out this common factor of 4, we get 1, 3, 3, 1. And the next one, pull out a 5, we get 1, 4, 6, 4, 1. So I think we'd recognize there's essentially a Pascal triangle appearing here in the denominators. So we can express that in the following way. We can first of all take out the common factor. So if we're in position nk, for example, maybe this one here. Let's say we're looking at this one here. Okay, so that would be in position 1, 3. Okay, so what is this common factor that we're taking out? Well, this would be in this this diagonal here. So there's a 1 and the 3. So we have to, I guess, pull out, what did we say? Pull out a 5. So 5 would be 1 plus 3 plus 1. So an n plus k plus 1 in the denominator. If we pull that out, then along this diagonal, we just have 1, 4, 6, 4, 1. So those are the binomial coefficients associated to 4. 1, 4, 6, 4, 1, which is the sum of the entries 1, 3. Okay, so what we're getting here in the denominator is a binomial coefficient. The binomial coefficient is the n plus k, choose, I guess, 1 here. So there'll be an n plus k, choose, well, either n or k. Here's the binomial coefficient, and we should take its inverse because it's appearing in the denominator. Okay, so that looks like some kind of formula for the general entry of this table. And it also makes a little bit clear that apart from the minus sign, there's a kind of a symmetry between the n's and the k's. That's a very nice formula. It's a surprise because typically we don't expect that the difference table will generally allow a pleasant formula to give you the general entry. That's rather special. And that's something that Leibniz appreciated, and he actually used it to a good extent to come up with some interesting formulas that we'll see later on in the course. One of the things that we're moving towards is to try to understand sequences in a more careful, precise way than usual. And we've isolated this idea of a k-sequence, which is a finite sequence, which is built on a chain. So we actually know where the positions of all the elements are. And in that context, I want to now refine our understanding of the difference operation. We can be a little bit more precise, and we can also separate the idea of a forward difference from a backward difference. They're very close, but sometimes it's convenient to have both of them at our disposal, as we'll see with the summation of parts formula. Okay, so let's illustrate things through an example. The idea is actually pretty simple. So we'll start with a sequence, okay? So here's a 5 sequence, actually. It has 5 elements. And the sequence elements are associated to natural numbers. These are the indices, okay? So it's actually built on the chain from -1 to 3. So here under n, I've just given you the underlying indices, and the sequence is built on top of that. So at -1 we have 4, at 0 we have 2, at 1 we have 3, at 2 we have -1, at 3 we have 7, and we don't have any other entries in this sequence, so it's very finite and bounded. Okay, so now associated to this sequence we can create some difference sequences, and we can do that in at least 2 different ways. So one is the forward difference that we've talked about. But now we can be a little bit more precise about what exactly the forward difference of this k sequence is. Here it is right here. So there's a delta of s, and here's what it is. So at -1, we look at the entry and the following entry, the one next to it. And we take the difference. So the next entry minus the one that we're at. So that's a 2 minus 4 gives us a -2. So we put a -2 there to represent that this is the difference between where we're at and the one following us. Similarly, here there's a difference of 1, the 3 minus 2. Here there's a difference of -4, the difference between -1 and 3. Here there's a difference of 8, 7 minus -1. And there's nothing here. Okay, we cannot put anything here because there is no next term in the sequence that we should take a difference of. So we're going to leave this empty. That means that the forward difference is 1 less in extent than the original sequence. We started with a 5 sequence, now we have a 4 sequence. But another thing that we could do is a variant of that is called a backward difference. Okay, so instead of looking this way, we look this way at the sequence. Okay, so how does that work? So we're looking at the same sequence. Now we're looking at a particular index, let's say the index 0, and we're looking at the difference between where we're at and the previous one. Okay, so now it's 2 minus 4 is -2. 3 minus 2 is 1, and that's put there. -1 minus 3 is -4, and 7 minus 1 is 8. So we're getting the same values as we do for the forward differences, but they're in different places. The whole thing has been moved over 1. And notably, we no longer have an entry in the -1 position because it doesn't make sense to ask what's the difference between where we're at and the previous one, because there is no previous one. And correspondingly, we do now have an entry in the last one because there is a difference, 7 minus -1. That's actually the difference at 3, the backward difference. Notationally, to get at the symmetry of these 2 differences, we use this upside down triangle for the backward difference. And this symbol is sometimes called nabla. Okay, and in LaTeX, this is the short form for it, so NABLA. Well, this one's slash delta. Okay, so the delta of S, it's a 4 sequence on -1, 2, while the backward difference, nabla of S, is a 4 sequence on 0, 3. So these differences are ending up on slightly different chains. Now I want to say a little bit about arithmetic with sequences. So when we're working with sequences, it's natural for us eventually to want to do arithmetic with them, to add them, subtract them, multiply them, and so on. And there's at least 2 different ways of doing this, which is a little bit making the subject a bit complicated, because in some ways we want to do things one way, and in other applications we might want to do things slightly differently. So because we want to be precise, I want to distinguish these 2 things. So I'm going to call them sequential arithmetic and polynumber arithmetic. And so the sequential arithmetic is perhaps the naive arithmetic, where you have operations of addition, subtraction, and multiplication on sequences. And they are pointwise operations, but only defined on common chains. So what that means is if you have 2 sequences, and so typically we're talking about k sequences, finite sequences of a certain length, because those we know exactly what we're talking about. But they are positioned possibly in different places. Okay, so you can have one sequence here and another sequence sort of over here. And then there's going to be possibly an overlap, a common domain or chain on which they're both defined. And it's on that common domain that we want to introduce the arithmetic of the 2 sequences. So we're only going to add them or subtract them or multiply them if they're both defined at the same spot that we're considering. If only one of them is defined, we'll leave the operation undefined. Okay, so we're going to call that sequential arithmetic. But there's another kind of approach where we think of the sequences as pretty close to being polynumbers. After all, we defined polynumbers originally in a sequence kind of fashion. And so it's often interesting to think of sequences as being some kind of like polynumbers, and then we can apply the polynumber operations to sequences. And although they are somewhat pointwise, the product is, the Cauchy product is not pointwise. And also these things are also defined even when the 2 sequences are not necessarily overlapping. Okay, so there's a bit of a distinction here, but both of them are important. In particular, this polynumber kind of arithmetic is important in linear time invariant theory, and also has lots of other applications. So we do want to ultimately consider both of them. But in today's lecture, we're only going to consider this sort of simpler one, I think, the sequential arithmetic, where we're strictly talking about pointwise operations, and the sequences have to be defined on the same indices in order for the operations to be defined. So this will be simplest to explain if I just give you an example. So let's talk about sequential arithmetic, and here are 2 sequences. And for reference, here are the indices that are positioning our elements. So we have sequence S, which is 4, 3, 4, 5, and it's supported on the chain from -1 to 2. Here is another sequence called T, sequence 2, -1, 1, 8, 6, whose indices are going from 0 to 4. So this would be kind of a standard sequence because it starts in the standard place of 0. But we don't always insist that sequences do that. But we do insist that we know exactly where the elements are in terms of our reference indices, which are always integers. Okay, so here's S and here's T. And let's look at the 3 operations of addition, subtraction, and multiplication of these 2 sequences. So it's a pointwise business, and therefore necessarily it's only happening on the common chain. So they're overlapping, and you can see that the common chain is essentially this one here. These 3 indices are supporting both elements of S and T. And so the operations are going to be only happening on that chain. Okay, the addition is pointwise. 3 plus 2 is 5. 4 plus -1 is 3. And 5 plus 1 is 6. So there is the sum of these 2 sequences, We don't put anything over here, 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 because there's no elements here to add. S minus t, so this one minus this one. 3 minus 2 is 1, 4 minus 1 is 5, and 5 minus 1 is 4. Again, nothing outside of that. And the product, pointwise product, 3 times 2 is 6, 4 times minus 1 is minus 4, 5 times 1 is 5. Okay, so those are the operations. And empty sequence values are not considered as 0. So we're not saying, oh, that's a 0 there, or there's 0 there. There's nothing there, rather than having 0. Okay. So this kind of sequential arithmetic, it satisfies the usual commutative, associative, and distributive laws. And to make it smoother, it's useful to introduce a sort of a degenerate kind of sequence, which we might call the empty sequence, maybe give it the name phi, which is a sequence which has nothing in it at all. Okay, a sequence which has nothing in it at all. So there's a picture of the sequence. There's no entries anywhere. But it's a kind of something that, that can be useful when we're doing this kind of arithmetic. Okay, so having this arithmetic, we can then define the difference and, well, the forward and the backward difference, and the summation on k sequences. And how can we do that? So here is sequence t, 2 minus 1, 1, 8, 6, on the chain 0, 1, 2, 3, and 4. And we've already talked about the forward difference and the backward difference, so let's just remind ourselves there. So the forward difference applied to this sequence will be minus 1 minus 2, that's minus 3. 1 minus minus 1, that's 2. 8 minus 1 is 7, and 6 minus 8 is minus 2. So there's the forward difference of this sequence. And the backward difference, the nabla, is the same kind of thing, but it starts here now. There's nothing at 0, but at 1 there's a minus 1 minus 2, which is minus 3, a 1 minus minus 1, an 8 minus 1, and a 6 minus 8, which is minus 2. And we can also define a summation of this finite sequence, where we do the same kind of thing as we did previously, but we start by sticking in a 0 at the first entry. So there's a 0 there, and then from then on we're adding the cumulative subsequences of the one we have. So the next one will be 2, and then 2 plus minus 1 is 1, and then 2 plus minus 1 plus 1 is 2, and then all of these together is going to be 10, and then all of these together is going to be 16. So we end up going a little bit further than the original sequence, is typical of what we get when we take the summation of a sequence. So we're starting with 0 and we're going one beyond what we've got. All right, so now I want to tell you about a very nice formula called summation by parts, which is a way for us to find sums of sequences. Finding differences is in some sense kind of easy because you're only taking differences of two things. But if you have some big sequence, finding a summation of it is getting onerous because you have to keep adding more and more terms. So it's nice to have some kind of technology for finding sums of sequences. It's a very important kind of problem in the discrete calculus. Okay, so let's suppose that we have two sequences, S and T, and they're finite sequences, maybe K and L sequences. And the crucial thing is that they overlap on a particular chain. So here's a representation of this picture. Okay, we have indices up here, and we have the sequence S here and the sequence T here. And maybe these sequences carry on outside what we're considering, but we're just considering this particular chain from M to N. So m, m plus 1, m plus 2, all the way up to n minus 1 and n. Okay? So we're sort of restricting our attention of these two sequences in this finite range. And we're assuming that both sequences are defined on this entire range, from m to n. Okay, so here is the way we're going to think about summation by parts. So it's a formula that involves two kinds of products. Well, there's two summations, and one of them involves a difference formula for one of the sequences, and the other one involves a difference formula for the other sequence. So here there's a forward difference for t, and here notably there's a backward difference for the other sequence s. Okay, so let's have a look at the formula. So it says that the sum from I equals m to n minus 1 of si times delta t sub I. Okay, let's just have a look at that first term. What does that mean? So the index is going from m to not quite n, all the way up to n minus 1. And what is it that we're summing? We're summing the products of the values of the sequence s, like si, times not the sequence t, but its forward difference. So the forward difference delta of t sub I. So when I is equal to m, we would take s sub m times, over here the corresponding thing would be the delta of t sub m, which would be t sub m plus 1 minus t sub m. That difference would be happening there. So we're taking products of values of s with differences from t, but they're forward differences. And since we're restricting ourselves in this range, we can only go up to n minus 1 because that's the last forward difference that we can create from the t sequence in this range. Okay? We can go up to n minus 1. Delta of t sub n minus 1 makes sense. That's the number t sub n minus t sub n minus 1. Anything beyond that would require us to go beyond what we can see in our window, and we can't compute that. So we're just sticking with what we can compute, and so this sum goes from m to n minus 1 and involves a forward difference of t. Okay, the next term in this formula is similar, but now we're taking differences of the s sequence multiplied by values of the t sequence. But notably, we're taking backward differences for the s's. So the indices are also a little bit different. Instead of going from m to n minus 1, we're now going from m plus 1 to n. Okay, so I is now running from m plus 1 to n. What are we summing? We're summing the product of the backward difference associated with s. So like the first term would be, this one here would be the sm plus 1 minus sm. That would be that term there, multiplied by the tm plus 1 value there. Okay, we do products of differences of the s's times values of the t's. And we're going from m plus 1 to n. And why are we going through that range? Well, it's because we can't go anything further. The first backward difference that is defined is this one here at m plus 1, giving sm plus 1 minus sm. There's no previous backward difference. Okay, so these are the maximum things that we can make of this form. And the statement is that if you take these two combinations of differences times sequences, that what you get is something pretty simple. You get the product of the last two elements in the sequence, namely Sn times Tn, minus the product of the initial ones, Sm times Tm. So this is going to be our summation by parts formula. Now in different textbooks it's stated sometimes a little bit different way, and the notation is sometimes a little bit different, and sometimes they don't use a forward and a backward difference, but we're going to find it congenial to use this particular form. I think it's perhaps a little bit easier to remember than some of the other forms, but still it does involve some remembering. Okay, so why is this formula working? So I want to explain that by giving it to you in a precise kind of example here, so you can see what the reason is. So here's the formula again. I've copied it again, and here are two sequences, S and T, and I'm assuming that the window now, just for illustration purposes, is between m equals 2 and n equals 5. So the sequence values that are of interest are S2 up to S5 and T2 up to T5. The sequences very well may continue, but we're not going to be using or looking at sequence values outside this window. Okay, so what happens now? Why is this formula true? So let's look at what happens to the left-hand side. So these two sums. What does the first sum look like in this case here? Well, we're going to sum from m to n minus 1. So in this case, that'll be from 2 to 4. And we're summing, well, values of s times differences, forward differences of t. So what that amounts to is S2 times T3 minus T2. That's that forward difference of t evaluated at 2. Okay, that's the first term. And then when I is 3, we get S3 times the forward difference T4 minus T3. And then when I is 4, we get S4 times T5 minus T4. And that's the end of this first sum. Okay, the second sum involves products of differences of the s's together with the corresponding t's. But we're going from m plus 1 to n. In other words, we're going from 3 to 5 now. Okay, so the first term will be, here's the 3 case. We take the backwards difference of s at 3, namely s3 minus s2, there it is, times t3. The next value, and we have I equals 4. We get S4 minus S3, that backwards difference, times T4. And finally, this last one, S5 minus S4 times T5. And the claim is that when we expand all of this out, there'll be lots of cancellation, and all that we'll get are just the product S5 T5, which is, there should be a 5 here, there we go. We get S5 T5 minus the product S2 T2. So the product of the last two entries and the product of the first two entries, we're taking the difference between those two products. Okay, so why is it true? Well, let's just have a look to see what happens when we expand things. So when we expand this thing out, there'll be cancellation. So the smallest terms values are the S2 with the minus T2. That's not going to be canceled. It's sitting right there. But the S2 times T3 will be canceled by this term here, minus S2 times T3. That'll cancel that one. Okay. The other term that's involving here is S3 times T3. And you see that's appearing up here with a minus sign. Also here we have an S3 T4, but that's occurring down here with a minus sign. Also occurring here is S4 times T4, but that's occurring up here with a minus sign. Also here's S4 times T5, which is occurring over here with a minus sign. So they all cancel, and the only thing that's left over here is an S5 T5. Okay, so I think the pattern is kind of clear. If we went further on, it's the same pattern. Things here cancel with that, and those things cancel. So everything cancels except for the very first term here and the very last term there. Okay, so this is a very useful tool for making sums. And it's especially interesting or useful when one of the sequences that we are considering is itself a summation. So suppose we, for example, we have h sub n, which is the summation of the sequence of reciprocals of natural numbers that Leibniz was interested in. So this is a very interesting and important kind of number, h sub n. 1 plus a half plus a third all the way up to 1 over n. It's called a harmonic number sometimes. Okay, and we might be interested in summing harmonic numbers. So the harmonic numbers are created from the sequence of reciprocals, but they themselves form a sequence. And so we could be interested in summing that sequence. For example, the sum from I equals 1 to n minus 1 of h sub I. We could ask, what is that? Is there a nice formula for it? All right, so let's have another look at that sequence of Leibniz, but now from the summation side of things. So we'll take the sequence of reciprocals of natural numbers and think about making a summation table for it as opposed to a difference table. So typically, of course, we expect this to be more work than creating a difference table, because with summations you have to do increasingly more work to sum up all the elements of the sequence right from the beginning. But let's just actually see what happens here. So there's the original sequence S there, and from that the next column will be the harmonic sequence, consisting of these HNs, which are the sums, 1 plus a half plus a third all the way up to 1 over n. So these are essentially the sums of the sequence over here. So for example, here's h sub 1, which is the sum of just this one here. Here's h sub 2, which is the sum of these. H sub 3, which is 11 over 6, sum of these first three. Then h sub 4, 25 over 12. h sub 5, 137 over 60, and it carries on. By convention, h0 equals 0. We always start our summations with a 0. Now, typically we would expect that the amount of work required for such a summation table is going to keep on increasing. Already at this level here, there's no easy way of obtaining one of these entries other than to actually perform the arithmetic of adding all these reciprocals together. But rather remarkably, when we move to the second column, a simplification, sort of a magical simplification, takes place. And it turns out that we can find these entries, which actually represent summations of these ones, relatively easily. Let me illustrate that, say, with this entry here. Here's 77 over 12, which is the sum of 0 plus 1 plus 3 halves plus 11 sixths plus 25 over 12. But instead of having to add up all of those, there's a fast way of getting this entry. And that's to take this entry here, which is 137 over 60, and subtract 1 from it. That would give us 77 over 60, and then to multiply by 5. That would be 77 over 12. Does the same thing work, say, over here? If we take 25 over 12 and we subtract 1, we get 13 over 12. We multiply by 4. Yes, indeed, we get 13 over 3. So this is a very pleasant aspect of this, suggesting at least that we can get this second column of the summation table relatively simply once we establish this kind of formula, which we can do through summation by parts. So here's the proposition that gives us that second column. It's that if h sub k is 1 plus a half plus a third all the way up to 1 over k, so often called the kth harmonic number, then the sum from k equals 1 to n minus 1 of h sub k is n times h sub n minus 1. Okay, so to prove this, we're going to use the summation by parts formula, and I've repeated it there. But in the special case where the interval is from 0 to n. And the two sequences that we're going to look at are, first of all, the sequence of the harmonic numbers, h0, h1, h2 up to hn. And then the second sequence is just the sequence of integers, 0, 1, 2 up to n. So this will be sequence S, this will be sequence T, and then the summation by parts formula has this expression. Sum from I equals 0 to n minus 1 of Si times the forward difference delta T sub I, plus the sum from 1 to n of backward difference of S times Ti. The sum of those two is the product of the last two entries, Sn times Tn, minus the product of the first entries, S0, T0. Okay, so let's see what this actually looks like when we put in these values here. Okay, summation I equals 0 to n minus 1. S sub I is just h sub I. Okay, and this forward difference delta T sub I, well, these are just integers, so the differences there are always 1, so we're always multiplying by 1 in this first sum. In the second sum, we're going from I equals 1 to n, and now we're taking the backward differences of the s's. That is, the backward differences of the h's. But the h's themselves are defined in terms of a summation. So if you take the difference between two successive elements like this, let's say you take h sub k and you subtract h sub k minus 1, then you're only going to get the 1 over k. All right? So that's pleasant. That means this term here is just 1 over I, because we're talking about the ith one. And the t sub I is just I. And then pleasantly, this product will just be 1 in each case. On the right-hand side, the product here is hn times n, and the product here is h0 times 0. So that'll disappear. So we get, over here, we get sum from I equals 1 to n minus 1 of h sub I, which is what we're interested in, equals, here there's an n times h sub n. This disappears. And this is just n, because we're summing from I equals 1 to n of 1, which is n. We bring it to the other side, there's a minus sign, and then n times h sub n minus 1. And that's a proof of this pleasant formula that allows us to get the second column of the summation table for the reciprocals of the natural numbers. And it might be a fun exercise to think about whether successive columns of this summation table are also accessible through some kind of magic like this. So there's much to learn. I'm Norman Wildberger. Thanks for listening.